All right, right off the bat, so after I paused the other video, I decided to check my work because it's always good to check your work. And obviously, or maybe you noticed during the previous video that like some of my answers were wrong, like especially when I got to the simplifying things with log rules. So I said natural log of 30 minus 65 is ln of 65 over 30. That's wrong. That should be 30 over 65. So that changes this to a 30 over 65. Also, when I did this and this, what I was doing was like doing the log rule x ln of a equals ln of a to the x, and I was applying that to the 1/5 and to the t. And I wrote my new exponent as 5t, but it should have been 1/5 times t, so t over 5 should have been my exponent as well. So good thing to check your work when you're doing this stuff. The way that I check my work is by going over to this equation that I get at the end. So this I believe is the correct equation, and I can check that by plugging in my my initial values of 0, t of 0 equals 135 and t of 5 equals 100. So if I plug in t equals 0, this exponent would be 0, and so this whole thing would just be 1. So I should get 70 plus 65, which is indeed 135. And if I have an exponent of 5 right there, then t over 5 becomes 5 over 5. So this becomes an exponent of 1. So this just becomes 65 times 30 over 65, basically with no exponent. And the 65s cancel. This becomes 30. 70 plus 30 is in fact 100. When you're plugging things in, if you're not getting things like 5 over 5 gives you a 1, and you just get like kind of gross looking things, and that's probably a sign that something went wrong. And so that's sort of what happened in my head. That was the red flag. And so that's what told me like, oh, well, I should review what I did and make sure that everything's like okay, because it didn't seem like I had the right numbers, and in fact I did not. So good to check your work, especially if you're recording a video and you're trying to do things like way too fast while explaining things. It's just easy to make mistakes. So good to check your work. Anyway, chapter 4 stuff. So I'm gonna just kind of go through the problems and then talk about anything that I think about as it comes up. Verify that this set forms a fundamental set for this differential equation. There are 2 parts there. You need to, 1, show that, I'm going to call these guys y1 and y2, show that these satisfy our differential equation, and we need to show that y1 and y2 are linearly independent. Maybe on an exam, I would, if I'm strapped for time, maybe I would only ask you to like show one of the 2 of them. Probably more likely to ask you to show this one because this is like the more important one, in my opinion, because this is basically chapter 1 stuff. So I'll verify it for y1, and then I'll just sort of, because I'm sure you get the idea if you know how to do one of them. So y1 is e to the negative 3x, y1 prime is negative 3 e to the negative 3x, y1 double prime is equal to negative 3 times negative 3 e to the negative 3x, so positive 9. That's our coefficient, and then plugging in to our differential equation, we get 9 e to the negative 3x plus 4 times negative 3. 4 times negative 3 is negative 12 e to the negative 3x, and then plus 3 times y, which is e to the negative 3x. So this is equal to 9 plus 3 of something minus 12 of something, which is equal to 0 of something. So it's satisfied. If you do the same thing for y2, it's going to end up working as well. I'll fill in this later when I do the solutions, but you get the idea. It should be 0. All right, so this is our first thing, and then to show that it's linearly independent, this is when the Wronskian comes into play. So remember that linearly independent means, well, if you were to take c1 times e to the negative x, c1 times y1 plus c2 times y2, that this is basically never equal to 0 for any c1 and c2 unless c1 and c2 are both 0. So this is what it means to be linearly independent, and the tricky way that we learn to show this is using the Wronskian. So you put y1 and y2 at the top. I guess the order should have been this way, but it's not going to end up mattering. And then you take the derivatives for the next row. Oh, sorry, that should be just -1. And then you do this times this minus this times this. So e to the negative 3x times e to the negative x, and then minus -3, so that's going to make that a positive, e to the negative 3x times e to the negative x. So we have -1 of this guy plus 3 of this guy, which is equal to +2 of that guy. And I could simplify that to e to the negative 4x. And because e to the negative 4x is never equal to 0, then we could be done. So don't stop here. It's not good to stop here, because at this point it is not clear algebraically why this is not equal to 0. So it needs to be clear from your expression why this expression is not actually equal to 0. It's clear from this step because e to the x is never equal to 0, so 2 times e to the x is never equal to 0, so 2 times e to the negative 4x is never equal to 0. So at this step, it's pretty clear that we can say it's not equal to 0. At this step, it's not really that clear. So simplify to get it to a step where it's clear that your Wronskian is non-zero. Okay. All right, so they're linearly independent, and so we're good. Yeah. All right, consider this differential equation. Let's find the complementary solution, and then find a particular solution, and then state the general solution. Complementary first, convert this to a polynomial. I'd like to put it up here. Okay, there's no first derivative, so this is just lambda squared minus 4. So this is lambda minus 2 times lambda plus 2 if I factor it. You could do the quadratic equation, and you would find that your two answers are plus and minus 2, and so it'd factor this way. But this is telling us that our y1 is e to the positive 2x, and our y2 is e to the negative 2x. So our complementary solution is equal to c1 times the y1 plus c2 times our y2. So this is our complementary solution. Find a particular solution to the differential equation. Okay, so here's where we do the guess or check method. So y sub p is equal to, all right, so this is a quadratic. So we're going to say ax squared plus bx plus c. And then we plug it into our differential equation. So we need to figure out what y double prime is. So y prime is 2ax plus b. Y sub p double prime is equal to 2a. So plugging into our left-hand side, which is L of y, I'm just going to use that notation from 4.1 that we talked about. So this is y double prime, just 2a, minus 4 times y and so I can simplify this. So this is negative 4a x squared minus 4bx plus 2a minus 4c, which equals 3x squared. All right. So this has to equal 3, and this and this have to equal 0. So negative 4a is equal to 3. A is equal to negative 3/4. Negative 4b is equal to 0, so b has to equal 0. And then 2a minus 4c is equal to 0, so 2 times a, which is negative 3/4, minus 4c equals 0. All right, so I can add this to the right-hand side, so I get, so that's like adding, this is 6 over 4, right? So this becomes 6 over 4 on the right-hand side, and 6 over 4 is the same as 3 over 2. And then divide by 4 to get c is negative 3/8. So y sub p is equal to ax squared plus bx plus c. Just using this, and then a is negative 3/4. B is 0, and then c is negative 3/8. So this is our particular solution. And so our general solution is equal to our complementary plus our particular, which was c1 e to the 2x plus c2 e to the negative 2x. If I copy that down right, yeah, I did. Okay, remember that right. And then plus our particular solution, which is, yeah, they're both negative. So we get that. Okay. All right, that's that. Remember, all right, so some other things to remember here. This 3x squared could be a couple, you can get like a couple different looking things. Like if this were sine of x or like sine of 2x, then your particular solution's form would be like a sine of 2x plus b cosine of 2x. If it was like e to the 4x, then your y sub p would be a times e to the 4x. If it was x e to the 4x, then it would be a e to the 4x plus b x e to the 4x, because you would have to have like this e to the 4x thing right here to accommodate for like, you know, terms that appear in like derivatives of this guy. And there are like a bunch of different like cases for like, you know, what else this could be. And there is also the weird case where, you know, if this were e to the 2x, so if I had e to the 2x here, then our y sub p would not be a e to the 2x, because this e to the 2x thing was already part of our complementary solution. So if this thing is not part of our complementary solution, then we don't have to worry about it. But if it is part of our complementary solution, then the fix is to just multiply it by x, or x squared, or x cubed, or whatever you have to multiply by to avoid any like duplicate terms in your complementary solution. Okay. Get rid of that. Great. Okay. 9y double prime plus y equals 3 secant of x over 3. All right, so this okay, so we can't do like the guess and check method to find a particular solution over here, because this secant thing is not of one of those forms that we could just guess and check for. It's just not going to work. So this is going to be one of those variation parameter ones. So we need to start off by finding our complementary solution. So we convert this to a polynomial. So 9 lambda squared plus 1. And how do you factor that? Well, you could okay, so this is basically a difference of squares. So I know how to factor this off the top of my head. The trick here would be to kind of think of this as like 9 lambda squared minus negative 1. So this is like, or or we could even write this as like 3 lambda squared minus negative 1, which is, and negative 1 is like I squared, right? So here we have 3 lambda squared, and here we have I squared, the square root of negative 1 squared, which gives you negative 1. So this factors as 3 lambda minus I times 3 lambda plus I. Okay, if you didn't follow that, that's fine. You can just do the quadratic formula. Quadratic formula says on this guy, we're going to get negative b plus minus square root of b squared minus 4ac all over 2a. And our b value is 0 here. So this is 0 plus or minus square root of 0 minus 4 times a times c. c is 1 all over 2 times a, which is 9. So this is plus or minus the square root of negative 36. So this is 36 in here. Square root of 36 is 6, but I have a negative in there, so it's 6i. And then this is over 18. Okay, so this tells us that this is equal to plus or minus, or I could say 0 plus or minus 1/3 of I. Okay, and we can get our roots like the same way up here, because this tells us that lambda is equal to I over 3 for the first one, and negative I over 3 for the second one, so we get the same answer in the end anyway. Now we can just say this is our alpha, this is our beta, and so our general solution, our y1 would be e to the alpha x cosine of beta x, and our y2 would be e to the alpha x sine of beta x, where this is our alpha and this is our beta. So our solution is going to be y sub c is equal to c1 times y1, and our y1, so alpha is 0, so e to the 0 times x is just e to the 0, which is 1, so I won't bother writing it there. And then cosine of beta x, and then beta is 1/3. And plus c2 times sine of beta x. Okay, and again, this is just equal to e to the 0, which is 1. Okay, if this was like 1 plus 1/3 I, then it would be like e to the x, e to the 1x or something. Okay. All right, let's find the particular solution. So this is where we do variation of parameters. I have these memorized at this point, but these are the formulas that we're working with. U1 is equal to W1 over W, and then integrate it, yada yada. So just make sure that you know how to do these. So the whole point is like our y sub p is equal to y1 times u1 plus y2 times u2. The order here doesn't really matter. This might not match what's up there, but again, it doesn't matter. So we need to figure out what our Wronskian is and then what our w1 and our w2 are. So we have our y1 and we have our y2. So our y1 is cosine of 1/3 x, and our y2 is sine of 1/3 x. Now we take our derivatives. Derivative of cosine is negative sine times, and then we're going to times by 1/3. Derivative of sine is cosine times the derivative of the inside, which is 1/3. All right, so this Wronskian, this gives us 1/3 times cosine squared of 1/3 x minus negative 1/3 sine squared of 1/3 x. Can factor out 1/3 from this. So a third times cosine squared plus sine squared is equal to 1, which equals 1. And so we're left with just 1/3. All right, W1 is I take my first column and replace it with my answer column. So I put a 0 and whatever my f of x is over there, and then I keep my second column the same. And what's our x? Okay, so I'm gonna get rid of this. Also, this is annoying. I'm going to make this a different color. Just gonna gray this out because you don't need to do it. Maybe I won't gray that out. Okay. And 3 secant of x over 3. All right, so this is our answer column, 0, and then just this guy for the bottom entry. So this is equal to 0, this times this, which is 0, minus this times this. So this is 3 sine of 1/3 x times secant of 1/3 x, which, let's see, this is equal to secant is 1 over cosine, which is equal to tangent. Okay. Cool. W2 is going to be cosine 1/3 x negative 1/3 sine of 1/3 x. So keep this column the same, and then second column will now be our answer column. So this is this times this, minus 0 times that. So this is just 3 cosine of x over 3 times secant of x over 3. And again, secant is 1 over cosine. So this is like cosine over cosine, which is just 1. So this is equal to 3. Awesome. So then u1 is equal to the integral of w1 over w, which is equal to the integral of negative 3 tangent of 1/3 x over w, which is 1/3 dx. So this is like equal to negative 9 times the integral of tangent of x over 3, which we're just conveniently told is equal to this. So 27 times that. And u2 is equal to the integral of w2 over w. This one I think is going to be a lot easier because it's just 3 over 1/3. So this is equal to 9. And then integrate 9, you get 9x. So then y sub p is equal to, let's see, what's our y1? Our y1 is cosine of 1/3 x times u1, which is 27 ln of cosine of x over 3, plus y2, which is, by the way, I'm applying this formula up here, which is, this is our y sub p, and then our y sub 2 is sine of 1/3 x. Times u2, which is 9x. Okay. Make sure that you don't flip your cosine and your sine, flip your like y1 and your y2. Like if this and this are in the wrong place, like if I wrote sine of 1/3 x times this plus cosine of 1/3 x times 9x, that would be incorrect. Like the order in which you do your y1 and your y2 affects like why like this W and the W1 and the W2 all look the way that they are. And so if you flip your Y1 and your Y2 in the end, like you're just going to get a different answer, and this would just end up being incorrect. All right, putting it all together, Y is just equal to our complementary plus our particular solution. Complementary is just what we found up here. I'm just going to copy and paste because I can. Shrink it. And plus this guy. Okay. And we don't multiply this guy by like C1 or C3 or anything weird like that. We just kind of keep it. All right. Variation of parameters problems are all kind of the same sort of deal. The integrals that you end up doing with like the W1 and the W2 to get your U1 and your U2, usually one of them is going to be like more straightforward than the other, but you know, make sure that you know your integration by parts and you know your U sub and all that good stuff. When you're doing like your Wronskians, make sure you know your basic derivatives. I cannot tell you how many people like when they had like x times e to the x up here, they just like forget how to do the product rule. Please make sure that you're doing your derivatives correctly and doing the product rule and doing all the chain rules correctly. It does matter, and it is going to affect your answer. And if you do like this, or this wrong to start, like, and you get to an integral that's just like impossible to do, then you probably messed up, or maybe your integral skills are not great. But yeah, just make sure that like all those basic fundamental skills are just like up to snuff. All right, is this the last problem? No, 2 more problems. Damn. Okay. All right, find the general solution of this differential equation. I think this one's like pretty quick, because this is homogeneous. So that's really just like finding the complementary solution, right? All right, I don't know how to factor this one, so we're gonna do quadratic formula. So negative b plus or minus square root of b squared, so 2 squared, minus 4 times a times c, all over 2 times a, 2 times 1. So this is negative 2 plus or minus square root of 4 minus 20, which is negative 16, all over 2. Oh my gosh, if you cancel out the 2 and the 2 and call this equal to the square root of negative 16, no, do not do this. I will be just upset with you. I get very upset when I see this. This is not correct. I see this more than I should in this class. Remember your basic fraction rules. You can split this up into 2 fractions. Plus or minus this. Please do not do this step incorrectly. Please do not cancel the 2 with the 2. Can't do it. We're adding up here and we're dividing up here. Addition and division do not cancel each other. All right, this is equal to negative 1 plus or minus the square root of 4i over 2. 4i over 2 is equal to 2i. All right, so this is our alpha, this is our beta. So our solution would be y equals c1 e to the alpha x times cosine of beta x plus c2 e to the alpha x times sine of beta x. All right, pretty similar to the previous one. So that's a quick one. All right, great. That's all we have to do for that one. I don't think we saw any examples here where we had like repeated roots. If you were to get like a repeated root, so just remember that if you like factor your thing and it comes out to like lambda minus 3 squared, that you would end up having like y1 is equal to e to the 3x and y2 would be equal to x e to the 3x. And if this were like even like a higher power, like if this is like to the 4th, then you would have like an x squared e to the 3x, and then like an x cubed e to the 3x for those things. So just remember all those like factoring rules and stuff like that. All right, anyway. Last problem. Reduction of order. So reduction of order is when we're given just like some initial differential equation, and we know one of them is just like handed to us, and we want to use that to get our second one. So this one I just definitely do not have memorized, and so this kind of have to be given this one. But this is our reduction of order formula. I'm going to copy it, bring it down here, and apply it. Okay, what's our p of x? Our p of x is just going to be whatever is attached to the y prime, assuming that we normalized. So if this was like 6y double prime, then you would have to divide by 6 first. If it were 6x times y double prime, then you'd have to divide by 6x. Just make sure that your coefficient of your y double prime is 1, and then your p is going to be whatever is attached to the y prime, including the sign. So this is like a -5, so our p of x is -5. So y2 is equal to y1. y1 is e to the 3x times the integral of e to the negative p of x. And then p of x is -5. So this becomes a +5, integrate with respect to x, over y1 squared. E to the 3x is our y1, and then we square it, dx. This is e to the 3x times the integral of e to the 5x, the integral of 5 is just 5x, over e to the 3x squared. When you raise an exponent to an exponent, they just multiply, so 3x times 2 is 6x. This is equal to e to the 3x times the integral of e to the 5x minus 6x. So this simplifies using exponent rules to, 5x things would cancel with 5x things down here, and you be left with like 1 over e to the x, which is e to the negative x. Oops. All right, and then we just integrate e to the negative x. The integral of e to the negative x is e to the negative x divided by -1. So same as times -1. So this is negative e to the 3x times e to the negative x. So this would be e to the 2x. So this would be our y sub 2. Okay. See. All right, so what's our general solution? Oh, did I forget to say the general solution somewhere? No, I think it's fine. Okay, anyway, our general solution is c1y1 plus c2y2. Now we just replace y1 with what we had, which was e to the 3x, plus c2 times y2, which was negative e to the 2x. I'm sort of absorbing this negative into this constant c2 right here. But if you wrote this as plus c2 times negative e to the 2x, or if you wrote it as like minus c2 e to the 2x, that would also be fine, but this is also correct. So that's your general solution. Yeah, these reduction of order problems are all going to be like fairly similar. These would be, it's usually just going to be like some simple differential equation here, and then, like this would be something that you'd be able to like find both of your solutions just like using the factorization thing. So this would be like lambda squared minus 5 lambda plus 6, which factors as lambda minus 3 times lambda minus 2. And so you should know that your solutions would be e to the 3x and e to the 2x. And we got negative e to the 2x, which is just a constant multiple of e to the 2x, which should make sense too, because we had like, just c2 times ry2. So this is like homogeneous, so you could just multiply any of your solutions by a constant and it'll still be a solution. So this negative doesn't really pose a problem or an issue or anything like that here. So just something to sort of be aware of. Yeah, let's see, is there anything else to sort of mention? I mean, there's definitely like more things that sort of happen in each of the sections, so still, you know, even if you understand everything in here, just make sure that you're like still studying and everything. Understand what a fundamental set is, the linearly independent stuff, the Wronskian. Yeah, I don't know if there's anything else helpful I can say. I don't know if this was even helpful to begin with because it's kind of long, but I don't know, hopefully you find it helpful. If it is, I can do this again for exam 3 in the final. If it's not, then maybe I'll do something else. All right.